Topological sorting. Now, topological sorting are for directed acyclic graph. Acyclic graph means they cannot have a cycle within that. And so here we are going to establish a linear order of vertices. And for every directed edge u to v, we should check that u comes before v in the ordering. Topological sorting is now possible only for DAGs. DAGs are the directed acyclic graph. So consider if this is the one of the graphs. I take 5. I cannot put 0 and 2 because if I put 0 then I could not put 4. So I put 5, 4 and then 2, 3, 1 and then I put 0. So here I am maintaining the property that if I have an edge from 4 to 0, 4 has to come before and 0 has to come later. So this is the whole idea of topological sorting. So topological sorting, initially I maintain a stack and then I mark all nodes as unvisited. For every node that is there, if it is not visited, I call the function DFS topological sorting. Now under this I will check if I'll mark that node as visited. For each neighbor of it, if it is not visited, I'll recursively call topological sorting and push it onto the stack. We will see the implementation of this.
हल्दी डालना.
So let us see the topological sorting. I have this graph. There is A to C. Let me do this. I will do this graph here. It is A to C. Also I have B. B is also coming to C. B is also coming to C. Then C to E. A to C, B to C, then B to D also. B to D, D to F, C to E. Yeah. So I have A to C, B to C. See, and now I cannot mark A, C, E because then I cannot put B. So this is the whole idea. And then, so this is my graph and I call topological sorting. So now this is the function. Now under topological sorting, I'll have a visited set and I'll also have a stack. Here I'm calling the other function, DFS function. I will add this so now this is another function which is defined within this. For every node in graph, if it is not visited, so it will take the first node. So in our case, it will call A. It is not in visited, so it will call DFS of node. Visited dot add of V. So now to the visited set, A will get added for every neighbor that is there. If it is not in visited, it will recursively call the DFS again. So here it's going to call DFS of B and DFS of C. and it will also append it to the stack. So now here it is calling DFS of C. Once it sees DFS of C, it will call DFS of, here this will get added here, it will call DFS of E. Now E will not have any neighbors. And so my final answer is going to be in stack only. So initially it included it will include so this is the result B, D, F and then A, C, E. This is the list. So initially when it will call for A, for C it will have two neighbors and so it will B and E. So initially A is added to the list and then that will recursively call C. That will recursively call for B and E. That will also get added to the visited. To the stack initially, let me print stack here each time. See, initially it is E which is getting added because it is not having any nodes. Then it is C which is getting added. I'm printing the reverse of the stack. Then it is C which is getting added. So it's like I'm going to the neighbor and then I'm taking the reverse of the stack. And then C is getting added here. And then the next one is A is getting added. Then it will move on to the other side. There B, D and F are there. So that will get added in the reverse order. So first of all F because it does not have any neighbor. D because all its neighbors are processed. And then finally B. And then it will print the reverse of the stack to get me the result. So this is basically the working of the graph.